Thank you, everybody, for joining us today. My name is Wendy Dietzler. I'm the Director of Events and Education for Trade Press Media Group. I want to thank you for joining today's webcast, Got Batteries? Key Concepts for Deploying NEC-Compliant Emergency Power. Our presenters today include Robert Benavides and Victor Bonaccia. Robert Benavides is the National New Energy Landscape Business Development Manager for ASCO Power Technologies. He began his career with ASCO in 2013 and has held several positions over the past 10 years, including sales, marketing, and strategy. His focus now resides in the new energy landscape. And that's where you're going to find the fast adoption of distributed energy resources, transitioning distribution system, that's the AC to DC transition, and the requirements of load management. Benny is focused on market trends, disruptions, and collaborating with Schneider Electric teams to solve the challenges faced by the partner and end user communities. Victor brings 13 years of experience from applications engineer to product management with an education in electrical engineering and engineering management. His expertise lies in standby power solutions, monitoring architectures, and he also has several patents in this space. He's been involved with the IEEE for 15 years, where he is currently a senior member and was awarded the 2019 IAS-PES Outstanding Engineer Award for North Jersey. Most recently, he was selected as one of Consulting Specifying Engineers 40 Under 40 Engineers in 2024. That is quite a resume. Today's webcast learning objectives. Let's go over those before you get to hear from our experts at the microphone. We're going to discuss which National Electric Code articles require grid isolation for inverter-controlled power sources, such as battery energy storage systems. We're going to go with BESS from now on. We're going to learn how the NEC enables BESSes to power standby and emergency loads directly. We're going to review the new UL 3008 outline of investigation for automatic interconnection switches for the emergency system builds. And finally, we'll discuss how newest automatic interconnection switches can really streamline the deployment of inverter-powered backup systems and optimize their costs. That's a nice 1-2 punch. But before we get started, just a couple more details to go over. As you heard our colleague Paul mention, we do encourage audience questions throughout the webcast. You're going to hover your mouse over to the bottom of our screen. You're going to see that Q&A button pop up. Go ahead and type in your questions at any time. We'll get to as many as possible. And later today, our event also includes a multiple choice polling question. You'll see that pop up as we're approaching our Q&A time. So your participation there is also greatly appreciated. And finally, at the conclusion of today's webcast, you're going to get a copy of today's presentation slide in PDF format. There will also be a link to a brief online assessment, which you can complete, pass, and receive a CEU certificate for your participation today. We're going to archive this webcast at facilitiesnet.com/webcasts. I'm going to take a break and let the real subject matter experts step up here. I'm going to pass it over to Victor.
Thank you. Thank you. Next slide, please. So as mentioned, what we're going to cover today, we're going to start off by looking at what's happening and what's shifting in the market and how that's driving changes in applications and therefore also codes and standards. Once we understand a little bit about what's changing in the codes and standards around using DERs and BESS systems and the requirements for isolation, we're going to go through some core architectures, going through a sequence of operations of how you expect those types of systems to function at the full facility level. And then once we're there, we're going to go back and cover some details on isolation devices and get back to the Q&A. So next slide. So what's happening out there right now in the market around battery energy storage, around resiliency, around renewables? Well, we're seeing a lot of things shifting. We're seeing energy density of batteries increasing. And while the energy density, meaning how much power can they store in a certain footprint, is increasing, at the same time, the cost of those sources is decreasing. Solar efficiency is improving, making it more and more of a viable value prop to implement solar as a renewable source in your facility and that kind of inverter-based source. And around these spaces and other similar spaces, there's other exotic pieces coming out, things like hydrogen fuel cell. Some places are using wind energy, maybe a little bit less common, but still happening. There's new technology evolving every day and maturing every day. Some of these are not necessarily new. They've been around for a while. but they're reaching a point where they're a lot more commonplace. The technology is people are feeling more comfortable with it as it's matured and has a proven track record behind it. But at the same time, as those technologies are evolving, the market's desires are evolving too. There's more of a desire for energy cost optimization. In the past, a lot of times people were only really focused around resilience beyond getting power from their utility, so they throw in a generator. But we're seeing a desire now to have equipment in their facility that's helping lower energy costs as energy costs go up, and people become more and more focused on green initiatives and sustainability initiatives to meet corporate targets. At the same time, that's not to say that the resilience application is going away. There's actually an increased need for resilience. So people want to save money, but at the same time, they also want their system to be more reliable, partly based on the fact that we're becoming more and more reliant on digital technology. 10 years ago, or let's say 20 years ago, people weren't as worried about data centers going down. It was an inconvenience. But today, a data center goes down, or any facility goes down, a cell tower goes down somewhere, it becomes a much bigger deal. We become more tied to our digital lives, the way we interact with our finances, the way even at a hospital, our patient records get transferred, not to mention the obvious pieces like the equipment in an ICU and things like that. So resiliency is becoming more and more important to our everyday lives. And there's also government subsidies now being funded and tax rebates being offered to implement some of the technologies around renewables, around sustainable sources, that makes it more attractive for people to apply these kinds of things. So we're seeing the market shift, we're seeing technology changes, but exactly what does that look like? So in the past, we were used to seeing a utility, maybe a generator. Now we're seeing a lot more like the sources I mentioned: battery energy storage, solar, etc. We used to be focused mostly on AC power. We had AC coming in or AC being generated, and that's being distributed down to the loads all the way. But now a lot of these sources are DC based, such as the batteries on an inverter system or the output from a solar panel. The downstream loads are also starting to mix between AC and DC. We're starting to see some data centers where the racks are actually taking DC inputs rather than AC directly to drive efficiencies. The energy flow is shifting. It used to be very hierarchical, where power flowed from the top down, meaning the utility through your distribution down to your loads. But now we're seeing actually the power flow in both directions, because a lot of times, if you think about that hierarchy of a distribution network, we're seeing things that can act as sources down by where the loads traditionally were. Things like solar is coming in from the bottom of your distribution system, battery energy storage. So things that were traditionally thought of as loads can actually be sources now as well. But beyond that, some of those, like battery energy storage, can actually be both. If it's charging, it's a load. If it's discharging, it's a source. And as I mentioned, there's now the higher desire for resiliency and economic optimization. So all these things are coming together, shifting the landscape of our electrical distribution architectures, and it's growing at an exploding rate, as you can see from the chart here. That's just the rate that we're seeing those adoptions taking place year to year, and we expect it to continue to grow. So what's that mean? It means that our architectures have to evolve with these technologies, and the agendas and goals of facility owners who want different priorities between resiliency and optimization. And along with that, codes and standards are always having to evolve as well to keep up with these changing technologies and these changing trends in the market. Next slide, please. The one noteworthy standard or code, I should say, that has changed in the National Electric Code is around what's an allowable device for standby power. So throughout the presentation, I'm going to be referring to several excerpts from National Electric Code and UL and various codes and standards. You'll see them referenced on the slide. But in this particular case, historically, energy storage systems, battery energy storage, beyond being used for UPS short-term applications, was either not mentioned in the code or in some applications specifically forbidden for extended to be used as an extended outage source of power. But in the most recent editions of the National Electric Code, that's now being allowed. And this excerpt from Article 700, which is around critical facilities, and you'll see similar phrasing in Article 701 and 702 and others. You can see that it's explicitly mentioning that energy storage systems, implying battery energy storage systems, are allowed now as sources for standby power. Beyond that, the code also goes to mention that the emergency sources, in this case, the battery storage system, can be used to operate in parallel with other sources. You see that on the right-hand side over here, specifically the normal source. Next slide. Now, where exactly does the parallel operation come into play? Well, we see it referenced in numerous other parts of the code where it basically says very similar phrasing. The emergency source shall be permitted to operate in parallel with the normal source. If we go down another one, the emergency source shall be permitted to operate in parallel. Again, pretty much the same phrasing. One step below that, interconnected microgrid systems shall be capable of operating in interactive mode, which is just a fancier way to basically say what it says in the top two as well, which is you could have your sources work in parallel with the utility when everything's okay. And that goes back to the point I made before about people wanting more than just resiliency from their emergency source. They also want to use it for economic optimization. So the code is allowing this. That's one major shift that's happened over the years. First, that the code allows you to use your standby power source for more than just standby power. You can use it in parallel with utility so that, for example, with a battery energy storage system, you can charge that system from your excess solar or when power is cheap, and then discharge it when it's expensive, which helps you save money by basically playing the utility rates against each other and save money and economic optimization through that method. So the first most important thing is people are now allowed to use renewable sources and distributed energy resources for standby power, and they're allowed to use it in parallel with utility, which is what you're going to want to be doing 99% of the time when you don't have an outage, to help you save money off your utility bill in the long run. Next slide. Well, that's great, but if we're using let's say a battery energy storage system in parallel with utility, I still want to be able to use it for resiliency, for standby power, for emergency operations if there is an outage of some kind. Well, there's some rules around how to accomplish this. First thing we got to understand, and we'll cover this during the sequence of operations side, is you have to make sure that you can isolate that equipment from the utility power source so it can come up in a grid forming mode rather than a grid synchronized mode without backfeeding the utility or overloading. That's just inherent to the operation of the equipment. But the National Electric Code goes further and states that, and I'll start at the bottom here, the system shall isolate the emergency system from all non-emergency loads when normal electric supply is interrupted and shall meet the requirements, blah, blah, blah. Well, let's summarize that. It's basically saying that if you have a, say, battery energy storage system that you're using in parallel with utility, but you want to use it for emergency standby power, when you have that outage, you want to kick it on as a standby source, it's got to be isolated from that utility, so it can't backfeed the utility or overload, as well as it has to be isolated together with those critical loads. So if you think about it almost like an emergency sub panel, you would want to isolate that panel from the upstream feeder so that it's isolated from utility, the rest of your facility, and now that battery system can kick back on in a grid forming mode and be your main power source for all the other loads on that emergency sub panel. So you would have those emergency loads as well as that battery energy storage feeding into that sub panel. Now, because it's isolated upstream on that feeder to that panel, it's not going to backfeed up into the utility. It's not going to overload by trying to provide power to more loads on that system on other boards that it can't meet. And it protects the overall system. So the code goes out and makes sure that people are aware that isolation is a requirement, which is very similar to transferring when you have transfer switches with the generators. The main difference being that when you have a transfer switch, you're always isolated the generator from the utility. But in this case, with isolation devices and interconnect devices, it means the same thing. You are actually paralleled with the utility until the moment you need standby power. In that case, it isolates the inverter-based source and those critical loads. Beyond that, that isolation function still has to happen within 10 seconds, as you can see on the top here, for those who are working in Article 700 type loads that have more stringent requirements on how quickly they have to be online and feeding power to those critical loads. Next slide. Here is an example of how that interconnect or isolation device would fit into the system. Again, this diagram is an excerpt from the National Electric Code, and it shows here they call it the microgrid interconnect device, isolation device. It means the same thing, and they're all synonyms. But you can see how it's being fed by numerous inverters, which could be your battery energy storage system, can be your solar, on the left-hand side there. And that those are serving as resiliency when there's an outage, but also bringing down your energy costs when you're tied to utility. And then on the very top right-hand side, you can see the AC loads, which basically are your critical loads that are being fed. So if that disconnects, it disconnects everything except your critical loads from those inverters, and you're good to go. Next slide. Now, okay, we've talked about the fact that we're allowed to use inverter-based sources for emergency power. We've talked about the need for isolation for if you are using one of those for both energy optimization and resiliency. But the National Electric Code in numerous spots goes a step further and says that these must be essentially UL listed. The exact phrasing, as you can see here, is the equipment shall be suitable for the intended use and shall be designed and installed to prevent inadvertent interconnection. Should have a field label applied, should be evaluated for the application and have a field label or be listed for the application. So that really means the product needs to be tested and qualified for its specific job. And that basically means in most applications, it needs to be UL or similarly listed with one of those agencies to a standard that is specific to the application in which it's being used, which is interconnect applications and resilience applications. You can't just take something and say it's listed to be used as a overcurrent protective device and use it for this application, even though it might have similar functions, because the requirements for the design and qualification of that is different. So it has to be a standard that is specific to the application of interconnection and isolation. And at the end of the day, to most of us, that means a UL label. Next slide. Well, if we need these products to be labeled, what exactly do we label them to? Historically, there were no standards around this, actually. But most recently, UL has actually worked on an outline of investigation, which is basically a standard for all intents and purposes. It's the preliminary steps to a full standard called UL 3008, which is specific to interconnect switching. And it's the first standard around this space. And it's for critical applications and emergency applications, similar to the way you would see a UL 1008 for a transfer switch. The similar naming between 1008 and 3008 is intentional because they are very similar standards for a very similar application. So the naming is meant to be together. This standard actually combines aspects of UL 1008 from a transfer switching point of view with generators, as well as UL 489, which is a circuit, the molded K circuit breaker standard, because isolation is really a single contactor device. You don't need two sets of contactors. It took inspiration in parts from both of these in terms of construction requirement, in terms of this, functionality and sequence of operation requirements, took aspects from both of them to create this new standard and the new need for this interconnect, which is slightly different than both of those, just drew inspiration from it. And the thing is, it's a very robust standard. If you actually, going back to the comparison to UL 1008, which is really the golden standard for transfer switching that everyone thinks about when they think about resiliency and standby power switching, it aligns more closely to that when it comes to the performance qualifications of the product than UL 49. Some of the tests that are included in there are things like cycle testing with and without load, overload testing if you're putting overcurrent on the equipment, temperature rise testing to make sure it can hold up, of course, short circuit and dielectric testing to make sure it can handle a downstream fault if one happens. But where it takes more inspiration from 1008 versus UL 49 is the fact that in UL 49, when you're qualifying a breaker, each of those tests can happen on a physically separate sample for the test. So each test you do, you're starting off with a pristine sample. Meanwhile, UL 1008, most of those tests actually have to happen on the same sample. So each time you go into a test, the sample is more beaten up from the previous test already. So it's a much more robust and difficult standard to pass, which results in a higher, more robust product and a higher level of reliability out of the product. So that's part of the reason why. Can a breaker provide isolation? Well, yes, it can, but not to the same levels as a UL 3008 qualified isolation device, which has the right controls, sequences, and performance for the interconnect application. And why would you expect any less when that's what you've always expected out of UL 1008 for your transfer switches, right? And so all these things come together, right? So the National Electric Code is now allowing inverter-based sources for standby power applications. It's requiring that isolation be put in place to allow it to operate properly when there is the need for resiliency instead of the need for energy cost optimization. But if you are putting an isolation device in, it must be listed and labeled for the specific application of interconnection and isolation. And that's been answered by UL 3008 at the new standard that these types of solutions can be listed to for applications such as Article 700 facilities and loads in a hospital, for example. And all that comes together. Next slide, please. To our version of the isolation switch, which we call Source Pact, which Benny, my colleague, will walk you through now.
Yeah, thanks, Victor. And again, thanks for sharing the updates here on the National Electric Code. So yeah, I'm Benny. I'll be talking here on the product Source Pack, specifically this automatic interconnection switch. And we like to use the analogy what an automatic transfer switch is to a generator, Source Pack is to a battery energy storage system. And what we mean by that, and we'll go through a couple of examples here, is today in the industry, there's not really a purpose-built product that's designed specifically to isolate from the primary service, have the controls within that device to communicate to the energy storage system that you're safely isolated and to enable battery resilience. And of course, why do you want to enable battery resilience is during your grid connected operation, which probably 99% of the time you're grid connected. You get the availability to call on a clear, more sustainable energy storage system to provide backup power. These inverters have very smart inverter characteristics. They can operate in a grid interactive, grid time mode, but also become their own anchor resource, creating their own voltage and frequency to provide backup power. This product helps streamline microgrid deployment, where you have a purpose-built product here that's designed specifically for isolation with the controller to sense voltage and frequency outage. As we described earlier, the UL 3008 listing is the first of its kind for an automatic interconnection switch, and it's designed with the testing criteria to be robust and ensure reliability in these systems, much like a transfer switch. And then, of course, the max potential of your energy storage systems. Energy storage systems can be a heavy capital expenditure, and just giving that, the characteristics of these smart inverters, you want to enable resilience in your battery storage systems if you're taking advantage of the energy cost optimization benefits. So, for fractional of cost, you can install an automatic interconnection switch to get those benefits in your microgrid system for resilience. So how does Source Pack work? So Source Pack comes with the motor operated breaker. And you see that there on the enclosure. That's on the bottom second half, and the top second half, it has a Source Pack controller. And this controller monitors the primary service, so it's monitoring voltage and frequency. And when it detects an abnormality in outage, depending on the parameter set, it will send a signal to the motorized breaker to open. At that point, we're opening and safely disconnecting from the primary service. That could be at the service disconnect, that could be downstream from your main switchboard. But essentially disconnecting from the primary service, we send a contact signal to the battery energy storage system. Those inverters tell them that, hey, we're safely disconnected. You can now enter a grid forming mode, or you can basically establish your own voltage and frequency and provide backup power. And the key benefit here is we're isolated from the primary service. We're doing that to ensure that there's no back feed upstream to utility workers in the event of outage, and you are enabling your microgrid system for resilience. You're not back feeding upstream to workers that are potentially doing maintenance work or repairs, and you're avoiding any backfeed scenarios or two different voltage and frequency sources damaging load. So it safely isolates a portion of your facility so that microgrid systems can provide power to those essential loads, as Victor talked about in the National Electric Code. Of course, when we're isolated, when utilities returned, that motorized breaker within Source Pack remains open. So once we detect voltage and frequency are acceptable, there's a time delay setting in the controller that allows us to decide when we reconnect back to utility. Once we decide to reconnect back to utility, we'll send a shutdown signal to the inverters in the battery energy storage system, telling them choose return, shut down. That motorized breaker will close once again, and then the inverters sense that there's an available anchor resource and synchronize to that source. So these are some core architectures we like to review with the audience here. So if you look at the battery only, this is the scenario where you have an incoming utility and downstream of that main switchboard, even connected to the main switchboard, you have an energy storage system. Now, this energy storage system is there, of course, to help offset utility costs for that energy optimization benefits. But if you install source pack or automatic interconnection switch downstream of your main switchboard, not only is that battery energy storage system is a load during normal operation, but you can also disconnect that load and basically make it a power source, provide power to those essential loads. And that's really the tricky part here of these energy storage systems, how you design your system that acts as a load during grid-tied operations, but you can disconnect that load, make it a power source to really power just those essential loads. And as you know, energy storage systems are sized for 3 to 4 hours of runtime on average, depending on the chemistry of the energy storage system. You can get longer runtime out of them. But mainly for National Electric Code, you need at least 2 hours. And on top of that, the more batteries you add, the longer the runtime, but it's something to consider. And this battery only architecture is the simplest, most sustainable here. You don't have a generator, and you're using, if you have a solar system there to charge that battery energy storage system, or if not, discharge one time or when you lose power and when rates are normally high. Then we go to the middle here. We have a battery and generator system where you have an automatic transfer switch and a source packed product that both operate independently. So think of it, utility main switchboard downstream. You have your ATS providing emergency power to your Article 700 loads. This can be fire pumps, elevators, things like that, where you want to have that equipment on emergency generator power. And then you have your automatic interconnection switch, or what we call source packed, connected to your battery energy storage system, where in the event of outage, you're disconnecting that battery system from your main switchboard and isolating those essential loads to provide backup power. So again, this works great for retrofits if you want to add on a PV energy storage system into your facility, but you don't want to add all custom switchboard or control. It's a great approach. And then to the right, we have our battery first scenario where you have your energy storage system connected to your main switchboard. And in this scenario, you can run a battery first where essentially source pack acts as a primary service disconnect. So when you lose power, the ATS is downstream of that main switchboard, will remain connected to source one. And what I mean by that is when you lose power, your energy storage system will come online as the primary emergency power source, and the ATS will stay connected to source one. So they'll see a momentary outage, but the ATS will stay connected. And that way you can deplete your battery energy storage system first before kicking on to generator. Essentially like an N+1 system. Again, more greenly, more sustainable emergency backup power option. So we're going to go through the battery only scenario. As I went through the operation briefly, source pack is designed to be downstream of the service disconnect or downstream of your main switchboard, where you can isolate those essential loads to your battery energy storage system. Again, the battery energy storage system can act as a load during grid-tied operation, but it can also act as a power source. And the clever way that source pack does is an automatic interconnection switch, where it automatically isolates from the primary service and allows those inverter-based resources to provide power solely to those essential loads, not throughout your entire facility. We can deplete that reserve a lot faster. So this is a battery-only scenario. We like to show this single line diagram. It still resonates well with the audience. So here we have an incoming utility that's feeding into a main switchboard. If you look to the far right, there is a source pack or automatic interconnection switch just upstream to the far right of the main switchboard. This is your point of interconnection. And then upstream of that source pack device, you have a switchboard. Essentially, this is what we call your emergency switchboard. It can be called your energy storage switchboard, where you have your energy storage system connected, but also your PV photovoltaic system connected with essential loads. So during grid type operation, utility is available. Your energy storage and PV system are operating in grid tied or grid interactive mode. Those essential loads are receiving power from your entire system. Now, in the event that load demand is low and your solar and battery energy storage system are exceeding load demand, that source pack is designed for reverse power applications. So if we need to send power back through the main switchboard to help offset some of those non-essential loads, source pack is rated to do so. The beauty behind this device, as I mentioned, is in the event of utility outage, your entire system here goes dark. The inverters and the photovoltaic and energy storage system are designed to shut down when you lose that anchor resource. So with that in mind, source pack detects that power has been lost, and those inverters essentially wait for a very basic level controller. Some people reference it as a microgrid controller, to send a signal to the inverter systems to come back online, or not become the emergency anchor resource to provide backup power. And that's what battery energy storage systems have the feature to do. They're smart inverters. So once we're disconnected from the primary service, that breaker, motorized breaker and source pack will open up. We'll send a signal to the inverter system, the energy storage system, to become the emergency anchor resource. Now it's providing backup power to that essential switchboard. At the same time, your PV system will recognize that we have an available anchor resource to parallel to that will come online. Now you're providing power to those essential loads in your switchboard during an utility outage. I think we did this all by solely adding automatic interconnection switch. You didn't have to add a specific and advanced microgrid controller to control all the utility main service disconnect. You did this being off the main switchboard and solely by segmenting those essential loads. Now, when utility is restored, source pack will detect that utility is available on source 1. Once we detect that utility is restored, there'll be a time delay. Source pack will send a shutdown signal to the energy storage system, telling them that, hey, utility's been restored, shut down. That battery energy storage, those inverters will not shut down. At the same time, your solar system also go in the dark. All those loads in the essential switchboard will lose power. Source pack will now reclose that breaker, so that breaker now will energize the upstream switchboards, and then once again, your battery energy storage system and solar system will sense that there's an available primary or anchor resource available and synchronize once again in that grid interactive or grid tied mode. So now we're going to go through the battery and generator architecture, and this is something I talked about in prior slides, where we have an ATS and source pack, both independent. In this scenario, have an ATS there. This could be an existing generator there that you want to have on emergency power for those, NEC 700-701 loads. We have your source pack, this automatic interconnection switch to power your optional standby loads. Again, both of them operate independently, and they provide emergency power and enable that in the generator, also an energy storage system for an emergency scenario. So this is the same single line diagram. The only difference here is we have a automatic transfer switch, and this is the same design. I'm showing this diagram here to highlight the benefits of having an existing generator and battery energy storage system. Both the systems operate independently. So what I mean by that is when we lose power, the ATS will sense that power has been lost, so will the source pack controller. Once we detect that utility's been lost, source pack will isolate. At the same time, the ATS will send a star signal to the generator. Inverters and a battery energy storage system, just inverters in general, operate very almost instantaneously. And what I mean by that is when they lose power, they can change state from a grid tie to a grid forming mode very quickly. They will come online much faster than a gen set. Once we detect that energy storage that the generator is available, the ATS will transfer. The ATS operates as a specified, has been doing so for close to a century now. Transfer over to generator. Now your emergency loads, NEC 700 loads are now on generator, and now your optional standby loads are on emergency power provided by the energy storage system. And of course, when utility is restored, both ATS and source pack operate as specified. They will remain, I guess, isolated in this situation where the ATS connected to source 2. Source pack will keep the motorized breaker open. We'll send another signal to the BESS to shut down. The ATS will do an in-phase transfer. We'll transfer the load within a specific parameter, make sure it's in phase so that the load don't experience a disruption or any rush current. And then once source pack reconnects, your energy storage system will come back online based to the grid tied operation as it was originally intended for the utility. And now your system is operating again in a grid tied fashion with both ATS and source pack providing power to those essential and optional standby loads. Now we'll go through a battery first scenario. So this is a use case where you'll have your energy storage system connected to your main switchboard. Source pack is there to serve basically as the service disconnect, is downstream of the service disconnect, and downstream of that main switchboard, you'll have your generator there. This is where you have that N+1 scenario where you can call in the battery energy storage system first to provide backup power. And of course, if that energy storage system were to deplete its reserve, you have the generator there to kick on as a secondary emergency power source, where the ATS is at that point transferred from source 1 to source 2. We'll go through an animation here on a design that we've worked with that's similar to this approach. So this design, we have an incoming utility. We have the main service disconnect. Downstream of the main service disconnect is our source pack automatic interconnection device feeding to a main bus. Now we have, if you look at that AC system there, that main bus, we have 2 PV arrays connected. So during grid tied operation, PV systems are in parallel, grid interactive, providing power to the system. We have our energy storage system as well. It's connected to this main bus, and we have 2 breakers for ATSs that are providing power to essential loads. In this scenario, when utility fails, the entire system goes dark. Again, those inverters, they shut down inherently. That's per code. So they're designed to shut down to prevent any backfeed. Once they shut down, source pack will detect the outage. Again, this outage time or the moment that breaker opens can be set to 0 to 6 seconds. In this scenario, you want to probably call on that battery energy storage system first. You can program that to 1 second or 0 seconds, where as soon as you lose power, that source pack device opens and sends a signal to the battery energy storage system, tell them, hey, we lost power. Change state from a grid interactive to grid forming mode. That energy storage system, again, will come online very fast, so the inverters operate quickly. Now your main bus is energized from battery power, and now your inverter system is able to come online, and those ATSs, again, it's happening instantaneously, stayed on source 1, and there's inhibit transfer contacts within the transfer switch to inhibit transfer to source 2. So still connected to source 1, and you'll remain connected to source 1 to the battery energy storage system until you since the utility has been restored. Now, when utility is restored, we'll go ahead and send the shutdown signal to the battery energy storage system. Again, source pack has that controller that sends when the utility is restored to shut down. Once the energy storage system is shut down, de-energizes, source pack will then at that point close its breaker. Upon closing, that main switchboard will re-energize the main bus in your system, where the ATSs again will sense that power has been restored to source 1. And again, you can also program the ATS controller so as soon as they lose power, they have the same time delay as a source pack device, where you can delay transfer to source 2 up to 6 seconds. And the same deal here for source pack. Once utility is restored, that main bus is not energized. You're again operating grid tied mode. Now we'll go through the same type of animation here, but this is probably the more prevalent and more preferred approach. where here we have utility fails. Your main bus will go dark. Source pack will isolate and signal the best. So again, we're going through the same animation here where we're calling on the best to be the primary emergency power source. Ideally, again, these energy storage systems are sized for 3 to 4 hours of runtime, some even larger. But in the event that an outage should occur larger than that, or for a longer duration, you would want that generator to be basically the secondary emergency power source in your system. So let's just say we go through this animation, your backup power through the energy storage system, your loads and ATS are still connected to source one. In the event that your battery energy storage system hits the low reserve, or it's coming close to the 10-20% of its state of charge, at that point, the energy storage system will shut down. And that's where your ATSs come in. And now your ATSs will now transfer from essentially source one, where that energy storage system was providing power to, now to generator, where it called on the generator. This could be like an inclement weather condition where they lost power. Anywhere where you have a situation where you completely depleted the reserve, the battery energy storage system, prefer calling on your diesel genset. And this is that N+1 redundancy that we're calling on here, where you have the battery first scenario, where you depleted the reserve, and then calling on that generator for that secondary power source. Source pack will now detect that utility has been restored. So this could be like an 8-hour-long outage. Once we detect that utility is restored, we'll send a signal to the battery energy storage system telling them we're about to enter a grid tight operating mode. The breaker will now close. The battery energy storage system, the PV orders will sense that the main bus is energized, so the PV and energy storage system will not come back online. At the same time, the ATSs are connected to source 2, so you have that isolation through the transfer switches. And again, the transfer switches, when they sense the utility has been restored, to either retransfer back to utility in an open or closed transition, depending on what's specified. And then the ATS send a stop signal, generator stop signal to the gensets to cool down. And this is the ideal scenario where you're designing a microgrid system with PV. You want to use the battery first for emergency power. Again, these energy storage systems can be sized to provide at least 2 hours of runtime. And if you have transfer switches there, you can provide the energy storage system to provide power to those legally required NEC 700, 701 loads throughout your system, with the generator as a secondary emergency power resource should that energy storage system or outage last longer than 3, 4, 5 hours. So who needs source packed? We like to start off with specifiers. This is a new product in the new industry, right? And to Victor's point, energy storage systems have just been accepted in the National Electric Code as an acceptable means for emergency standby power. So with this, a lot of education on the UL listing, how the product is applied. This is an automatic interconnection switch. It's a little different than a transfer switch, but it entails all the same testing criteria and robustness that goes into a transfer switch testing product. So it starts with the consulting engineers to really understand how this product is used and designed in these type of applications. And then it goes to the contractors, where it gives less strain and complexity for the contractor to install this device. Again, this is a purpose-built device. It has the controller to sense when voltage and frequency have been lost, but also communicate to the energy storage system to enable that resiliency scenario that you would want in an energy storage system in the event of an outage. Purpose-built product. And for facility managers, it helps enable the ease and more importantly, the design of a microgrid system. So if you're installing a PV or have thoughts of adding on a energy storage system to your facility and don't want to retrofit existing breakers or add a complicated PLC, the energy storage, our source pack interconnection product, can be installed downstream of one of a spare breaker to install and add on that PV or energy storage system to your facility with ease. And if you have more questions about our product, here's our QR code. There you'll find a lot of our product specs, brochures, and white papers on the product. Again, it's key to differentiate, what's unique about the automatic interconnection switch. You'll find more information there on the UL listing as well. So right now we'll open it up. We'll send it back over to Wendy here to wrap things up.
Great. Thanks, Benny. Thank you so much for that presentation, to you and Victor as well. Well, as promised, everybody, you've been sending us questions, but first we'd like to ask one of you. You'll see a polling question pop up on the screen. We'd love participation, and as many of you as possible, just go ahead and cast your vote. It's that time of year. So go ahead and get that going. And while you are voting, we are going to jump into questions. We did see some really good ones come through, so thanks in advance. And Victor, I think you saw a few coming through and kind of put your hat in the ring for some of these. So we're going to start with those. There's a question on the front end about the instances where we recommend the use of UPS over the emergency power source. Is that something you want to tackle right away?
Yeah, I can talk to it. So I think the question was alluding to the difference in when should I use a UPS versus a battery energy storage system. And it's really about duration. UPSs are really intended to be very short bursts of power, short duration, high power usually, basically to hold you over until a more traditional long-term standby source can come up, like a standby generator. A battery energy storage system, although it's very similar, the basic components of it being an inverter, batteries, and a charge controller. The chemistries of the batteries are different. The design of the inverter and the way it handles heat dissipation and things like that are different. And it's designed more for a long-term power supply. And there are differences in the way those UPSs versus battery energy storage systems are constructed, where a battery energy storage system is meant to provide a long-term power in the world of hours instead of minutes, which is what you would expect from a UPS. So at the end of the day, it just depends on duration. They are very similar technologies, but when you get deep into the design, they do differ. And for that, it means they're better equipped to handle short versus long duration. And that's really what it comes down to.
Okay, great. Thank you, Victor. Here's a question I can actually answer. So I'm going to take this one. They're wanting to know if the slides are available. Yes. All the information that was shared here today, and it is so excellent, will be sent in a PDF format to everybody who attended today's webcast. You'll get that within about 24 hours or so. And you can always go back and watch this again at facilitiesnet.com/webcasts. But Victor, I'm going to pull you up again for this part of the question. And that is, people are asking about the availability of a Schneider and or ASCO paper or brochure on the UL 4008 NEC 705 source pack. So anything you want to speak to there that we could help point them toward?
Yeah, we have plenty of documentation on source packed and the associated standards, UL 3008 being the one for interconnecting and isolation up on the ASCO Power website. And considering it is one of our newer products, it's front and center on our website, so it's easy to find. So just check out ascopower.com and you'll find it there for sure.
Okay,
Yeah,
fantastic.
I'll also add to that, if you want to check out more details of the UL 2008 listing, it's also available on UL's website, and the same thing for National Electric Code for specifically details on Article 705, where you can find the relative information we covered there online as well.
That's great. Okay, so a lot of resources available for our audience today. Thank you. I'm going to ask a question about the BESS side of things. Peyton is asking if there's an option where the generator can charge the BESS if there's a delayed outage. Any insight into that?
Either of us can take that. I guess I'll go first, then Benny, you can jump in if you want to add stuff to it. The short version is yes. I've personally done some jobs, and actually, I think we have a case study on back to the ASCO Power website on a job we did like that, where we had it was basically a 3-source system setup. We had a utility source, of course. We had a battery energy storage system as secondary, together with some solar. And then on the third was the standby generator. So the whole the whole sequence at a high level was utility power goes out, it goes to battery energy storage power, and it prioritized that. If it ran down battery power to the point that the batteries were at a low charge state and you were getting the low battery alarm, basically, it would then kick on the generator, and the facility would run on the generator while the generator was also simultaneously charging the batteries. And then whenever the batteries were fully charged, the generator would shut off again and run on batteries until either utility came back or the batteries needed charge again and go through the same cycle again. So the short version is yes, definitely. We've seen it, we've done it, and I think it's going to be a common use case out there.
Yeah, to Victor's point, I mean, there's different ways to design a microgrid, right? And if you want to have the generator or battery energy storage system as your primary or secondary power source, there's ways to design that with automatic transfer switches. If that's not the right solution or the desired sequence of operation, we can always go with an intelligent switchboard. Uh,
Oop,
Maybe. Not sure
I
if
think we
that was
lost
just
him.
a pause or more than a
Yeah.
pause.
with
I think we dropped Benny drop. If I can finish the thought, I think it was
Okay.
going with that we have different there's different architectures you can use to approach that, right? You can do some of them with isolation, some of them you can do with ATS switching, some of them there are solutions with custom switchboards and control switchboards out there that we
Right.
can do as well. So it's all of course dependent to the site and the need and the application. But there's numerous approaches we can take for sure to meet that need.
Oh, that's great. Well, I think it sounds like there are some people who have some more specific questions. Jeff is asking about contact information. So Victor, I can either have you share here, but in addition, we will make sure that information is in the follow-up email that everyone gets as well. But he was specific about looking for best solutions in emergency settings. So a little more of the
Yeah.
same.
Hopefully you hit yes to the survey question that just popped up a few minutes ago, because
Right.
that'll get us a connection back to you. And I wish Benny was still here, because Benny is the sales guy who heads that up. So we'll be sure to track you down and get any questions answered that you may have.
That
I'm
sounds great.
you guys don't need
Uh,
me here. I think it's a brief
Yay.
you're back
interrupt.
now?
Yeah.
Cool.
Great. All right. Well, let's jump through a couple more questions. Somebody's asking about how big of a facility in watts can these batteries handle, for how long? Somebody's giving some very specific wattage of 1500 watts at 140 amps on a diesel generator right now. Any kind of way they can draw some kind of baseline against that?
Benny?
I would say, I mean, for energy storage systems, I mean, we're dealing primarily behind the meter. So I would say,
Okay.
what we're dealing with is like 100 kW all the way to 500 kW battery energy storage systems. Now some go larger than that. I've seen a megawatt, 2 megawatts, 1 megawatt energy storage system. So it really depends. And with these energy storage systems, they have an energy rate, also a capacity, a power and capacity rating. What I mean by that is the amount of runtime based on that uh, power rating. So if it's a 250 kW system, most of them have maybe like a 1250 kilowatt hour runtime. So you do the math behind that, they could last for up to 4, 5, 6 hours. So it really depends, but that's really what we ask for a building load profile to understand
Yeah.
what size best makes sense, and then we can size that based off your load profile to make sure you have the right amount of runtime for that emergency standby application.
Sounds like you have to crunch some numbers there. In terms of EV chargers, Victor or Benny, I'm not sure if you saw a more detailed question that came through from Jonathan. Maybe take a look at that, or maybe just speak to kind of the application on the EV side of things. What are you seeing? What are some of the advantages that people can take advantage of?
Yeah, I did see that question come in, and I kind of read through it. Again, let's follow up afterwards for a more
Yeah.
detailed conversation. But the gist of it, if I'm reading this correctly, is it sounds like there's a situation that's becoming commonplace out there where you have an EV with a dedicated utility, you have a nearby building with a microgrid that is backed up. And what you want is that when power goes down on the EVs from their main utility, you want to switch them over to the microgrid of the building, which could still be up since it sounds like it has some resiliency sources on it. The short version is that yes, I don't see any reason why that wouldn't be possible. Exact solution depends on the architecture in the one line, but from what I'm reading, and again, making a lot of assumptions on here, we'd have to look at a one line and talk through it more. I think in this case, a standard transfer switch would actually work with your utility of the EV itself being the primary source of the ATS and the preferred source, but then having that microgrid be the secondary source. So utility fails, and as long as there's power on that secondary source, that ATS is going to switch over to that other building's microgrid And then that would be feeding the load downstream, which is the EV chargers, right? Depending on the one line, it may need to be service entrance rated and things like that. But that's really getting to the nitty gritty. We'd have to take a closer look. But I think there are solutions. I think between source packed and basic ATS switching, we can meet that need if I'm understanding that one correctly.
Thank you for that. We're coming up to the top of the hour, which means we're coming up to our end of our time together, but we have time for one or two more questions. One, you were talking about source packed. Let's talk a little bit about the UL 3008 or 3008 listing. How does that address safety and reliability concerns in these modern power distribution systems?
So UL 3008, like any UL standard, really has a focus on two pieces: the performance electrically of the equipment itself, and there's all sorts of testing that goes into it, like endurance, meaning number of cycles and operations it can do. How can it handle a short circuit to make sure if there is a fault downstream that our equipment further upstream isn't going to be the point of failure in the system. The endurance testing, make sure that you can get, you're not going to operate it twice and it's going to break down. It can operate several thousand times for the expected life of the equipment, and it's going to hold up. So depending on various things like capacity, there's different metrics and all that you have to test to and prove that the equipment's going to perform to that level on the electrical performance side to make sure it's got a long, healthy life, and that when it's exposed even to what they call known, what's the phrase? A known fault condition, right? When it's a known adverse condition that is commonplace, like a short circuit for electrical equipment, that it's gonna not fail, or even with certain products, if it does fail in a safe way, right? So the standards govern all that, not just for UL 3008, but that's true for any UL standard for any piece of electrical equipment. The other side to it is the sequence of operation. So it makes sure that certain functions of the equipment that are critical for the safe operation within a larger system, make sure that those are well defined, tested, and implemented in a way consistent with these types of systems. For example, in UL 3008 and source packed, one of those points is you never want to connect two sources that are not synchronized to each other. For example, if the battery energy storage is still in grid forming mode, and your utility returns, you cannot close that isolation device, the source packed, until either you're synchronized, which is out of scope for source packed, or until you know that the battery energy storage has turned off and gone back to a grid time mode, and it's waiting to synchronize to the new source. So it's basically connecting to a dead bus. So the UL standard calls out requirements like that, and you must test and prove that you're meeting those requirements for safety. That way you're not implementing sequences that could knowingly be harmful to the overall facility.
Thank you. That was a super thorough answer, and I really appreciate that. I appreciate both of your time today. Robert, Benny, thank you. We definitely had experts behind the mic today. And a reminder to all of our participants today that all of this information is coming your way within about 24 hours via email, so keep an eye out. I'd like to thank everybody for joining us today. It's an important topic, and as we've seen, certainly the weather events happening any time of year, but certainly most recently, the need for that emergency power, that reliability, and that safety is only going to become more and more critical. So I'd like to thank you all for giving us this information and a path forward. And I'd like to thank ASCO for supporting this important message as well, and for their sponsorship of this event. But with that, we will wrap up our webcast. Thank everyone again for their time and wish you all a great day. This concludes today's webcast.
Thank you.